a wormhole, just so people can understand it. If you look at space and time, we've learned ever since Einstein in 1916, when he advanced the general theory of relativity, which is the modern understanding of gravity. We learned that gravity is the curvature of space-time. And what you do is when you are falling towards something, you are simply sliding along the fabric of your space-time towards whatever it was that you were saying is attracting you. And so it's a different construct from just action at a distance. You're there, I'm here, we have gravity, we pull each other, and that's it. It's a whole other thing going on. And if you think of space and time as fabric, then you can distort the fabric with the force of gravity. If you ask yourself, can I distort it in interesting ways that might benefit what I want to do in the universe? I can get you around among the planets using the rockets that we've got, and I can get you there before you die. Alright, moving around the solar system takes days to the moon, months to Mars, years to the outer planets, and maybe 1 or 2 decades to Pluto. If you want to visit other stars, then every way we know to get there exceeds the human life expectancy. So you have to find a way to shorten that journey, knowing that the speed of light is not just a good idea, it's the law. There's a speed limit to how fast you can move in that fabric of space and time. The nearest star is 4 light years away. At the speed of light, you watch someone go at the speed of light, it'll take them 4 years. To do that, you say, okay, well, let's just do that then. But we're nowhere near the speed of light. Alright, this is, so it's hopeless, and that's the nearest star. Is there a way, maybe you can poke a hole through, or open up a hole in the fabric of space and time in a way that it's curved such that you can take a shortcut from one location to another. So imagine if you had a sheet so compress everything to a sheet, because otherwise it's hard to think of bending 4 dimensions. So our universe is now a sheet. So when I take that sheet, normally I'd have to travel the full length of the sheet to get from A to B, and I want to do that before the TV commercial, okay? And so what do? You warp the space, and then open up a hole from one side to the other where the 2 places are close in this higher dimension. And by doing so, you basically take this portal through, come out the other side, unfold the page. It basically, and the no time part is, well, how much did you warp the space in order to do that? And if you warp it a lot, it can happen basically instantly, like walking through a doorway. Or if it's warped a little less, then it'll take you a little longer. But in all cases, your effective speed is way greater than the speed of light, because you basically cheated. It's one thing to have a black hole where all space and time collapses on itself to a singularity, but what you now want is a hole through the fabric of space that remains open. And the configuration of matter and energy to create a hole is unstable against collapse. So, in other words, you can have a stable black hole there that's sucking in it, then distorting the fabric of space and time. But a wormhole requires actively holding it up so that while you're in there, it doesn't collapse on you, where you made one that's stable. See, we gotta learn the secret engineering of that. So the thing is, a black hole, most understandings of a black hole have you dying if you fall in. If you can pry open a worm, because you end up at the singularity, smushed and spaghettified and stretched and been broken. But a wormhole, if it's opened and maintained, it could do one of several things. It could be a hole to another part of our own universe, which is what you've just done, because you curved your universe and you're just going from one location to another. Or you can imagine wormholing out of our universe into another universe. So in that case, you'd have to print 2 of those and have 2 of their sort of coily hole structures intersect, and that way people in one universe would go through that and show up in another universe. Now the cool part is if you break the wormhole and collapse it, then you left your universe never to return again. So wormholes are fascinating, and of course they show up in so many different movies, alright? In Bill and Ted's Excellent Adventure, their time-traveling phone booth is basically a wormhole. In the movie Back to the Future, they don't appear to be traveling, it is a wormhole, but it's a portal, rather than an actual extended wormhole. They just exit one time and enter into another, right? And one flaw, but I'll give it to them because it did so much else right, in Back to the Future is when they leave the parking lot and end up, this is Back to the Future 1, they leave the park at 88 miles an hour, right? And they show up in the cornfield, in the farm fields that would become that strip mall. What they didn't factor in is that between those two times, Earth would have moved in its orbit. You can't only travel back in time. You have to also travel back in space if you want to land where you expect to land from where you left. So if you would have time traveled back and landed in the vacuum of space and they all would have died and the movie would have lasted 15 minutes, your wormhole, if it's going to go anywhere you want it, it's got to go somewhere. Otherwise, it's not only in time, but in space. All right, you want to make sure that it works out that way. So also is that movie in Time Bandits. That was what's that from the 80s? That one was the Monty Python crew. So that one was wormholes. In the movie Contact, Jodie Foster basically goes through a wormhole. And so, it's kind of fun cinematically to display one of these, to portray them as you're going through, and it's basically like a tunnel. And in a way, maybe the old TV show Time Tunnel was an earlier concept of a wormhole, although at that time I don't think we had the term yet for it. By the way, one of the earliest statements about the existence of wormholes was the idea that if a black hole absorbs everything that comes near it, let's take a look at the math surrounding the black hole, and you find out that there are two solutions to that equation that gives you the black hole. One of them absorbs everything, and one emits everything. Okay, so something that emits everything at all times is a time-reversed black hole. So you can ask, where does everything go that enters a black hole? Maybe it's what's coming out on the other side, which we'll call a white hole. How would you connect them? You connect them with a wormhole. So wormholes have very high utility. If you try to think about fun and interesting and useful bendings of the fabrics of space and time, and you got a damn printer that'll make that every day. I want to talk about the sun, the color of the sun. So here's the thing. If you're a school child and you to draw a scene and you want to put the sun in the sky, what crayon do you reach for? That's always yellow. And this notion has been with us since childhood, that the sun is yellow. That's not true. It's not even close to being true. The sun in broad daylight is too bright to look at, all right, without risking damaging your eye. When is the time most people ever find themselves looking directly at the sun? When is that? Not only do we have the yellow crayon in our crayon box from childhood, anytime we actually ever find ourselves looking at the sun, either on purpose or by accident, it's low on the horizon. The sun is rising or setting, right? It has a deep yellow color. Sometimes it's so deep it can be red, the amber into red. And we know the sun isn't red. Of course it's not red. You know intuitively it's not red, but somehow you don't know intuitively that it's also not yellow. Okay? What color is the sun? It is white. I can give you evidence of this if you need evidence, but I'm simply saying that as the sun gets, let's look at Earth, and it is the atmosphere wrapped around the Earth. The sun is directly overhead or anywhere near directly overhead. It goes to sort of, let's call that one thickness of atmosphere, okay, top to bottom. As the sun gets lower and lower in the sky, the path of light through the atmosphere is longer, okay, because now there's that angle through it. And the lower the sun gets on the sky, the more and more atmosphere it has to pass through. And in fact, you can calculate how many equivalent atmospheres it went through. Okay, and you just need a little bit of trigonometry. It's a simple calculation. And if it's low on the horizon, it goes through 5, 6, 10 equivalent atmospheres when it's low on the horizon. So whatever the atmosphere is doing to the sun when it's high up overhead, it's doing it 10 times that and more when it goes lower on the horizon. So let's see what the atmosphere is doing when the sun is overhead. In comes white light. And white light is composed of colors, as Isaac Newton demonstrated. All the colors of the rainbow: red, orange, yellow, green, blue, indigo if you must, violet. So in it comes particles in Earth's atmosphere that happen to be the same size as the wavelength of light of the blue side of the spectrum, the blue, indigo, purple, the violet side of the spectrum. Those particles preferentially scatter the blue out of the sunlight. Preferentially scatters it. So it subtracts away a little bit, just a little bit. Alright? The rest of the light makes it all the way to Earth's surface. But some of the blue gets scattered, and that's why we have a blue sky. The blue sky is stolen sunlight that would have otherwise passed straight through. Now, let's have the sun get a little lower in the sky. Will there be more of this going on? Okay, more of the sky. That's why on cloudless days into sunset, the sun gets deeper and deeper and deeper blue. The bluest sky, that's why sky blue is light blue, right? You want to talk about serious ride home to mama blue is the blue sky that surrounds the twilight curtain of a sunset. Now you're talking blue, right? Okay, so much blue is taken out that we now, Roy G. Biv, red, orange, yellow, green, blue, and he took out blue, indigo, violet. What's left? Red, orange, yellow, green, okay? If you add those colors together, you're gonna get an amber sun. And depending on how many particles there are, you'll get a red sun or you'll get a simple yellow sun right on the horizon. And so you would now look and say, oh, we have a yellow star. Look, it's yellow. Oh, no, it's the atmosphere made it yellow. It's lying to you. And here's what you do. At broad daylight, if there's thin cirrus clouds, okay, so it's safer to look up to the sun in the middle of the day. Is it yellow? It is white. The clouds themselves don't change the color of the sun. It just dims it. So you look at a slightly dimmer sun, behind the thin clouds as they pass. It's not yellow. Not only that, consider the following. Alright, now this takes a little extra thinking. And we in another explainer, we address this, but now there's a different reason for it. If I have a sheet of paper, and it's white, that means light reflected from it is an even mixture, an equal mixture of red, orange, yellow, green, blue, violet. All those colors together in optics makes white. So the fact that the page is white means all of those colors of light are hitting that page. So that when they reflect up, you see white. So a white light illuminating a white piece of paper shows up to you as a white piece of paper. Now, white reflects all colors. Let me put a red gel in front of the light. Now look at the paper. What color is it? It's red. So it reflects all colors, but now it's only getting red. It's going to reflect the red. It reflects all colors. The page is red. Okay, let's put a blue gel. What happens to the page? The page is blue. If the sun were yellow, then snow will be yellow. The fact that snow looks white is evidence that it's being illuminated by white light. That white light is either sunlight or a moonlight. It's reflected sunlight. So I'm just trying to be honest. I'm just trying to put it out there. White is the sun relative to incandescent bulbs. Your kids will have no memory of incandescent bulbs, but old-timers, if you're over 25, you're an old-timer, you remember bulbs that would get hot when you put them in, incandescent bulbs when you turn them on. The temperature of the filament is not as high as the temperature of the surface of the sun. And so the higher the temperature, the more full that spectrum becomes. So if you looked at the spectrum of a bulb in your house, or an incandescent bulb, it's very weak in the blue section. There's some blue there, which is why blue still looks blue under that light. but the blue is very weak under an incandescent light bulb. Okay? So, if you bring out film that needs the full complement of blue, and you take a picture under incandescent lights, everything is going to be red. That film, if it needed the blue, is called daylight film. This is why there was a difference. Again, I'm only talking old-timers here. There was indoor film and tungsten film and outdoor film. And the outdoor film was color balanced to get the entire spectrum of the sunlight. If you took indoor film and put it outside, that indoor film is too sensitive to blue because it's making up for the feeble blue coming out of a bulb. And it goes out and it's getting all the blue it ever wanted. If you have indoor film, took a picture outside, everything looks blue. Because it was hypersensitive to blue. And the sun has plenty of it. Okay, so, to a photographer, sunlight is blue. It's highly blue. And they have to correct for that. If they're going from indoors to outdoors, they have to redo the color balance on a white sheet of paper to account for the difference between indoor lighting and outdoor lighting. Now here's where they all got it wrong. But they're not going to change it because they're deep into it. You ready? If an artist draws an Arctic scene, what color is prevalent? Blue, right? If an artist draws Dante's Hell, what color is prevalent? Red and orange. Okay, so emotionally, we think of blue as cold and red as hot. Photographers will tell you we need to reduce the temperature of the light, which means make it colder emotionally. But the only way to do that is to get more blue in it, which means upping the temperature of the tungsten that they have shining on you, or to put more blue into it. And in the old days, that meant a hotter light bulb. So they said we need a cooler scene. They had to have a hotter bulb. We need a warmer scene. They had to have a colder bulb to do that. And that language is still embedded in that entire profession. The opposites, and they meet in the middle, and they deal with it. The moon's orbit. Again, I'm assuming that's what he's referring to, because the moon doesn't have a wobble that anyone cares about. So that's what. But there's an interesting libration. So what's happening is, because the moon's orbit around the Earth is not a perfect circle, okay, it's an ellipse. I can get as close as 225,000 or so miles, and as far as almost 250,000 miles. So it's a 25,000 mile range between when it's closest and when it's farthest. Okay, the moon is also tidally locked to Earth, so it's always showing the same face. Okay, that's a natural phenomenon in the universe, and systems of orbiting objects naturally descend into that state relative to each other. So that's fine. No, nothing weird going on there. Here's the problem. Okay, if it were a perfectly circular orbit, you would only ever see exactly the same side, and it's locked. You would only ever see exactly the same side towards you. Okay, here's the problem. When your orbit is not circular, when it's elliptical, you are moving faster in your orbit when you're closer and slower in your orbit when you're farther away. So, the point is, if you were tidally locked and in a perfectly circular orbit, for every little bit around the Earth you revolve, you will rotate a little bit, always keeping that same face pointed. So everything works out. But if you're going a little faster than average or a little slower than average, that little bit that you rotate doesn't line up as it would if you were in a perfectly circular orbit. It lines up on average, but if you're sort of fast in your orbit, then that little bit that you turn doesn't quite compensate for how far you've gone around the Earth. And if you're slow in your orbit, you haven't quite turned enough. When you look at time-lapse photos of the moon, it is striking to behold. The moon is like, it's like turning a little to the left to you, a little to the right, so we can see more than 50% of its surface over the duration of a month. That's true anytime you have a rotating object where it's not perfectly spherical. If there's a slight bit of mass off to the side, then there are extra torques on it, and that'll sort of bob as it turns. We wobble on our axis because of forces that are tugging on us, such as the moon, as we rotate and as we go around the sun. So you do get this sort of wobbling and bobbing. But for me, the fun thing is the libration, Google libration of the moon, and look at the time-lapse video. It's striking because you don't get to see it that way, because we see the moon once a night or once a day, and when you time-lapse it for a month, the dude knows that however fixed the stars look like they are on the night sky, in fact they are moving through space. And obviously the farther away something is, the less from day to day you're going to notice that it's moving. That's true on Earth as well. This is what led to the old childhood concept where you say, Mommy, Daddy, why is the moon following me? It's as you walk down the street, because the trees go by and the buildings go by and the moon is just there. Well, if you kept walking for 1,000,000 more miles, you would leave the moon far behind. You're just not walking far enough for something that distant to reveal the fact that you're walking past it. So the farther away something is, the less obvious its motion is to you. Okay? So so we have all the stars in the night sky, and they are part of the solar neighborhood. We're all orbiting sort of the center of the galaxy together, but even with that sort of community movement, there is movement among us. Okay, if you go back 75,000 years, we were anatomically human. I believe that's sort of early Homo sapien. 100,000 years ago, you would not recognize most of the constellations of the night sky. I would say about half the stars that are nearby us that trace out the constellations, they'd be in a completely different place. So, for example, the Big Dipper, which we know of as looking like where is it in England? Is it called all the stars of the Big Dipper, believe it or not, are part of a coherent star cluster, which is really close. So you don't think of them as a tight cluster. But so they're all sort of together, and they're moving in their own sort of orbits. And the Big Dipper would get flattened out. It turns out we've done the math on this, wouldn't recognize it as a Big Dipper at all. It's on Mars, where the temperature and the air pressure, the atmospheric pressure, are just right. That water, if you lived there, water would freeze, melt, and boil all at the same time. You can have a bowl of water with ice cubes in it, and the water is boiling. And that's stable, though that it's called a triple point. And water has a triple point of atmospheric pressure and temperature, where all states, 3 states of matter, can coexist happily. And so, yeah, that's why you can say water is liquid. No, water is only liquid when you make it a liquid. Okay, right? Otherwise it's solid or gaseous. So terraforming is you take a dead planet, and then you seed the atmosphere with aerosols, or you introduce microbes that will thrive on the carbon dioxide and might output oxygen, and then you step back and let it run its thing if you put in the right cocktail, and then out comes an arable green planet that you just terraformed. That's not an impossible dream. Earth was terraformed early on by Earth itself, right? So the question is, can you do it fast? Because Mars does not have a magnetic field, which would then shield it from solar wind, whose energy can break apart molecules, or have ozone that would protect it from ultraviolet. All of these, without these protections, life on Earth, we don't know how you would sustain it. Okay, that's fine. Consider that if you're living underground, none of that matters. Shield yourself from the sun, none of that matters. First of all, you can just shield yourself from it. Second, if we have the power of geoengineering to turn Mars into an arable place, I don't see why we couldn't figure out some way to deflect the solar wind or to block out UV. I'm not worried. That's like an engineering challenge, and engineers tend to solve problems when given the task. And so I'm not worried about that. It's the rest that is way more complex. We know how to block UV. We know how to block the solar wind. We don't know how to send in microbes and come back 10 years later and then have a forest. We just don't know how to do that. That's where the challenges are right now. If you have good geoengineering, you might find a way to stir up the Martian core so that it can then generate another magnetic field. I mean, what's stopping us? The full moon at night is crazy bright. In fact, it's something like 6 times brighter than a half moon. Because of the way the laws of reflection work, I think it'd only be like twice as bright as even brighter. So, on a moonless night, the unaided eye can see a couple of thousand stars. If the moon is out, you can see a couple hundred stars, so it drops it by a factor of 10. So if you're trying to see the deep universe, we have what's called dark time at telescopes, and it's highly competitive to gain access to a telescope while the moon is not up. Okay, it's called dark time. And then people who are on the brink of the detection of things will ask for dark time. So then we learned, well, why be on Earth at all? Why? Okay, but if you go into orbit, the moon is still there, okay? Now, the sky is not as bright, but it's still you don't want to look near the moon. You have scattered light into your telescope beam. So, how about 1,000,000 miles on the other side of the moon? How about that? That's where the James Webb Space Telescope is going. So it's far away from Earth and from the moon. And so, yeah, we're doing our darndest to get rid of the interference that we're now experiencing. But let me stay at it. There's radio interference, and we have radio wave telescopes. So what are we going to do about that? There's all this talk, whole conferences given unto putting radio telescopes on the far side of the moon, because the moon only shows one face. So if you're on the far side, you will never see Earth, ever. Okay, so that famous photo of Earthrise over the moon by Apollo 8, okay, Earth doesn't rise on the moon. It never does. It's either always there or never there, because you're either on the side of the moon that faces Earth or the side of the moon that faces elsewhere. And so the reason why that's called Earthrise is because they were orbiting the moon. And when you're orbiting, then the sky moves but rises and sets, and so they caught the rising Earth on the lunar landscape. So it's legitimately Earth rising. It's just highly misleading. So we are thinking about that, and it is a big problem. And so wherever the electromagnetic spectrum is noisiest, we try to do our darndest to avoid it. And sometimes it means going into space to the far side of the moon and even into deep space itself. Voyager, we turn off the switch after it exited the influence of the sun. There's everyone thinking, oh, the solar system ends at Pluto or Neptune. No, the solar system keeps going. All right, and one way to think about it is, as long as you're near enough to the sun to feel its sort of magnetic field and other effects, you say, I'm part of the solar system, right? But the galaxy has a magnetic field also. So if you start getting farther and farther away from the sun, the strength of the sun's magnetic field drops, and the strength relative to the strength of the galactic magnetic field. You reach a point. Oh, by the way, it's not just magnetic field, but the particle stream emanating from the sun relative to the ambient particle stream in the galaxy. You reach a point where you can no longer tell the difference between those two. Bada bing, you've left the solar system. Any amount of mass, you can calculate how small it would have to be, how compressed it would have to be for it to become a black hole. So if you wanted Earth to become a black hole, you'd have to shrink it down to like the size of a plum. Last I did the math on that. So if you manage to do that, bada bing, you have an Earth black hole. The point is, a lower mass black hole is smaller than a higher mass black hole. If a black hole begins losing mass, it gets smaller and becomes the black hole size appropriate for the amount of mass it has. It's always going to be a black hole. If for some magic force of nature, the black hole evaporates according to Hawking radiation, which your guy clearly knows about, and somehow did not get smaller, there would be a point where the density would no longer allow it to be a black hole, because it's about the density, it's not about the mass, right? And then the black hole would slowly reveal itself as a solid object. If one day we could manipulate the laws of physics, then we could reach into a black hole, somehow prop up its shape, so that as it got less and less mass, the density would drop, and then we could reveal what's inside. But then, at that point, you're no longer looking inside a black hole, are you? You're just looking at a regular object. And you know what happens? As the black hole continues to evaporate, the energy range that gets emitted becomes higher and higher and higher. So, large black holes are emitting like radio waves, and smaller black holes will emit visible light. The tiniest of black holes will emit gamma rays, and it has to do with the size of the black hole, whether the wave that it emits can fit inside the black hole or not. That's the quantum physics of it. Hawking worked all this out. Point is, as it gets smaller and smaller and smaller and smaller, the very last bit, oh, by the way, as it gets smaller, the rate at which it gives off energy increases. Okay, so this becomes a runaway process where it gets smaller and smaller, faster and faster and faster. And the very last moment, it happens catastrophically, and you get a little burst of gamma rays. So the original Hawking radiation paper prompted people to look for little bursts of gamma rays, like in the universe, which could signal black holes dying, having completely evaporated. We do see bursts of gamma rays, but they don't match the spectrum of a dying black hole. But there it is. This is our universe we all live in. It's a beautiful place.